Good day, everyone. Our topic for Chapter 3 is financial forecasting. Financial statement analysis helps us understand a company's past performance, but managers also need to anticipate what may happen in the future. This is where forecasting becomes important. Forecasting is the projection of future business variables, such as sales, revenues, earnings, costs, and other possible business conditions. Its main objective is to reduce the risk and uncertainty involved in decision-making. Before production begins, management must estimate expected sales and use available information to develop a strategic plan. Forecasting helps management plan production, inventory, factory overhead, sales, labor, and financing. The future is uncertain, so decisions cannot be based on certainty. Forecasting provides a reasonable basis for planning and resource allocation. Therefore, forecasting is a starting point for business planning and an important function in effective business operations. For this chapter, we have 5 major learning objectives. First, we should be able to define forecasting. Second, we should identify its different uses. Third, we should explain why forecasting is essential in financial planning. Fourth, we should differentiate the tools used in forecasting. Finally, we should apply forecasting tools and techniques. Now, let us identify the major users of forecasts. Top management uses forecasts for long-range planning, performance targets, strategic objectives, and capital budgeting. The production manager uses them to determine raw materials, production budgets, schedules, inventory, labor requirements, and shipments. The purchasing manager forecasts the quantity of materials needed to avoid overstocking or understocking. The marketing manager estimates expected sales and promotional activities. The finance manager forecasts cash inflows, cash outflows, and financing requirements. Finally, the human resource manager determines staffing requirements. There are 2 general approaches to forecasting: qualitative or judgmental forecasts and quantitative forecasts. Qualitative forecasting uses human judgment. It considers the decision-maker's intuition, emotions, personal experiences, and value systems. This approach is particularly useful when forecasting short-term situations or when sufficient numerical data are unavailable. Quantitative forecasting, on the other hand, uses mathematical models based on historical data and causal variables. It provides a more objective basis for forecasting. The chapter identifies several qualitative methods. These include expert opinions, the Delphi method, sales force polling, consumer market surveys, and PERT-derived forecasts. Expert opinion gathers knowledgeable individuals to develop a consensus forecast, but bias can affect the result. The Delphi method also uses experts, but their opinions are collected individually through questionnaires to reduce peer and group pressure. The sales force polling method uses sales personnel to develop sales forecasts. Salespeople have direct contact with customers, so they understand market conditions. Each salesperson estimates sales for a specific area. The estimates are reviewed, combined at the district level, and then combined nationally to produce a general sales forecast. Its advantages include simplicity, practicality, direct feedback, and useful information classified by segment, product, region, or individual. Another qualitative technique is the consumer market survey. Companies may survey existing or potential customers to obtain information for purchasing and planning. Surveys may be conducted through telephone inquiries, questionnaires, or interviews. Quantitative forecasts use mathematical models and rely on historical data or causal variables. They are divided into time series forecasting and associative or causal models. Time series forecasting is based on the assumption that the future is a function of the past. Historical observations are arranged according to equal periods, such as daily, weekly, monthly, quarterly, or annual periods. The important characteristic is that forecasting focuses on the historical behavior of the variable being forecast. A time series can be decomposed into 4 major components. The first is trend, which represents the long-term upward or downward movement. The second is seasonality, which represents patterns that repeat within a shorter and regular period. The third is cycle, which refers to patterns occurring over several years and is often related to business cycles. Finally, random variations are irregular changes caused by chance or unexpected events. Understanding these four components helps managers improve forecasting accuracy and make better decisions. The naive model is one of the simplest forecasting methods. Its basic assumption is that demand in the next period will equal demand in the most recent period. The formula is YT plus 1 equals YT, where the forecast for the next period equals the actual value of the current period. Because of its simplicity, the naive model can serve as a benchmark model. If another forecasting method cannot perform better than the naive model, that method may not provide much additional value. Its advantages include low development cost, no need for sophisticated software, simple data storage, easy operation, and no complex mathematical requirements. However, it does not explain causal relationships and may fail to capture dramatic changes. In the example, December 2019 sales of 5,750 become the January 2020 forecast. If January actual sales become 6,250, that becomes the February forecast. The moving average is another simple time series forecasting method. It uses the most recent observations to calculate the forecast for the next period. The manager must first determine the number of periods, represented by N, to include in the average. All observations included receive equal weights. The formula is the sum of the most recent demand observations divided by the number of observations. For example, a 3-month moving average uses the sales from the previous 3 months to forecast the following month. In the example, the April forecast uses January, February, and March sales, resulting in 14.00. The forecast is updated whenever new information becomes available. Moving averages are easy to understand and help smooth short-term fluctuations. However, they require historical records and may not respond quickly to significant changes or emerging trends. The weighted moving average, or WMA, improves on the simple moving average by assigning different weights to different observations. More recent data can receive greater importance because recent conditions may better represent the current market. The formula is WMA is sum of WI/DI, where WI represents the assigned weight and DI represents demand for the period. An important rule is that all weights must add up to 1.00. In the example, the weights are 0.20 for 3 months ago, 0.30 for 2 months ago, and 0.50 for last month. Using these weights, the April forecast is 14.10. The resulting weighted forecasts differ from the simple moving average because recent observations have greater influence. The method can improve forecast accuracy, but moving averages may still become less sensitive to real changes, require historical records.
Exponential smoothing is another quantitative forecasting technique. It is similar to a weighted moving average because it gives greater importance to recent data. The basic idea is that the future depends more heavily on the recent past than on the distant past. The smoothing constant is represented by alpha, and its value ranges from 0 to 1. A higher alpha gives greater weight to recent actual data, making the forecast respond more quickly to changes. A lower alpha produces a smoother forecast and responds more slowly. The formula is nu equals YOLD plus 1 minus alpha, YOLD. Here, YOLD is the most recent actual value, YOLD is the previous smooth forecast, and alpha is the smoothing constant. The appropriate alpha should be selected by comparing forecasting errors and choosing the value that produces the smallest error. To evaluate forecasting accuracy, the chapter uses mean squared error, or MSE. MSE measures the average of squared forecasting errors. Because the errors are squared, larger errors receive greater importance. The objective is to identify the value of alpha that minimizes MSE. In the example, the initial forecast is based on the 5-period average, producing 113.60. Using alpha equals 0.70, Subsequent forecasts are calculated by combining 70% of the most recent actual sales with 30% of the previous forecast. The process continues for each succeeding period. The resulting squared differences are then totaled and divided according to the MSE formula. For alpha equals 0.70, the chapter obtains an MSE of 48.28. A lower MSE indicates a more accurate forecast among the alternatives being compared. The chapter demonstrates why we should not simply assume that a particular smoothing constant is best. When alpha equals 0.60, the calculated MSE is 44.22, compared with 48.28 for alpha equals 0.70. Since 44.22 is lower, alpha equals 0.60 provides the better forecast among these two alternatives. The key lesson is to test different alpha values and select the one producing the lowest forecasting error. The page then introduces trend projection, which fits a trend line to historical data and extends that line into the future. It is useful for medium and long-range forecasting. The chapter also introduces associative or causal models, which consider variables that influence the variable being forecast. For example, sales may be related to advertising, demand to price, or sales to income or payroll. These relationships can support better planning. Linear regression examines the relationship between a dependent variable and an independent variable. The dependent variable is what we want to predict, while the independent variable helps explain or predict changes in the dependent variable. The basic regression equation is y equals a plus bx. Here, a is the y-intercept, b is the slope, and x is the independent variable. The slope represents the rate of change in y for a one-unit change in x. The chapter uses the example of nodal construction company, where sales are related to local payroll in Quezon City. The least squares method determines the line that best fits the observed data by minimizing the total squared errors. The important point is that regression does not simply examine time. It examines a relationship between variables and can therefore be used to estimate sales based on expected payroll levels. This final page demonstrates how the regression equation is constructed and then used for forecasting. First, we calculate the required totals and means. The mean of x is 3.0, while the mean of y is 2.5. Next, the least squares calculation produces a slope, b, of 0.25. The intercept is calculated using a equals y minus bx, resulting in 1.75. Therefore, the estimated regression equation is y equals 1.75 plus 0.25x. This means that the predicted sales can be estimated using the expected local payroll. If the expected payroll is 600 million Cuban pesos, the corresponding x value is 6. Substituting this into the equation gives y equals 1.75 plus 0.25, 6, equals 3.25. Based on the chapter's interpretation, the estimated sales are 325,000 Cuban pesos. The key lesson is that regression converts the relationship between variables into a usable forecasting equation.